All right, and then we heard from Wolfram about his new approach to physics based really on interactions and how those interactions propagate. And he feels he's been able to replicate quantum behavior and also the behavior of general relativity. And he's continuing to work on that. So it's very intriguing. Hopefully he's going to think about how to generate energy through his model that we currently just don't understand how to generate. So that brings us to today, where we're going to be discussing vacuum fluctuations and oscillations, potential ways of maybe generating forces from the vacuum, and then also some, how do we analyze this? We have Yoichiro from Stanford is going to talk about fluctuation dissipation theorem, and that's a common way of analyzing that. And then we have Lawrence Ford from Tufts University is going to talk about his approach to analyzing vacuum fluctuations. And then we'll have some discussion of some other models, pilot wave models based on De Broglie work. And Sonny White's going to close out the day talking about his dynamic vacuum model and the work associated with that. So that's just a little background of what we're going to talk about. And starting out the day is going to be myself, and I'm going to talk about some of our work in vacuum fluctuation forces. So let me share my screen. And I think I should put it on speaker view. Can everyone see my charts okay?
Yes, I got them.
Okay. Okay, great. Right, so this is an area that we at the UnLAB we've been working on. Can we generate forces from the vacuum or energy from the vacuum? And so first is a little bit of background about vacuum fluctuations. And again, these are, some of the words that could definitely be better. There's a lot of different ways of referring to the vacuum. There's the quantum vacuum, the ground state, 0-point energy. In electromagnetics, we often refer to it as the continuum, things coupled to the continuum. Well, what does that really mean? That means the vacuum. And people used to call it the ether. Maybe it still should be called the ether. Not really sure, but the vacuum shows up everywhere, really. So it's the ground state of a quantum oscillator. It's the lowest state that is possible. It shows up very strongly in Planck's law. So you always have at least the vacuum fluctuations in a black body distribution. The Casimir force is an indication of the vacuum fluctuations, and I'm sure everyone's aware of that, but this is a case where if you have a geometry, a physical object, you exclude some of the modes of the vacuum from in between in the object, in the middle of the object, and that generates a force. It's kind of like same as when a ship is close to a dock and some of the waves are not there between the ship and the dock. It generates a force that causes the ship to hit the dock. It's the same thing here. And it could potentially be very large. So 1 atmosphere pressure to 10 nanometer plate separation. Most of the forces measured are really small. People have not actually measured that value. Also in quantum chromodynamics, 99% of mass is from quark and gluon vacuum fluctuations. So the lattice theory that people have developed is based on mass coming from vacuum fluctuations. And it really has to do with fluctuating dipoles. So there is a range between van der Waals forces where it's just dipoles in a material interacting with each other, to the Casimir-Polder force where it's a dipole and a plate, to the Casimir force, which is different it is based on fluctuating dipoles, but there's also the retarded aspect of the fluctuations, the waves going back and forth. So the Casimir force falls off much less rapidly than the van der Waals force. This is, I think, the 6th power. This is to the 4th power. And there's many observed phenomena that has been attributed to vacuum fluctuations, like spontaneous emission, Casimir forces, things like the Lamb shift, fundamental noise, the dynamic Casimir effect, where you have a moving object, you can generate photons, and people have generated that, demonstrated that, the magnetic moment of the electron, etc. So many phenomena has been attributed to vacuum fluctuations, but I think it's important to remember that there's still debate about, are vacuum fluctuations real or not? And I say real enough. And, there's this the cosmological constant mystery, where from what we measure, the vacuum energy of free space is 10 to the minus 9th joules. But what QED predicts is that it's 120 orders of magnitude larger. That's based on a Planck scale cutoff. It depends upon where you cut off the vacuum fluctuations. But if you take the smallest value, it's 120 orders of magnitude. So something is missing, something is off there. And as Nick mentioned yesterday, you can attribute these vacuum effects either to the source field radiation reaction. So a radiation reaction, when something radiates, there's a response to that, or vacuum fields. And it depends upon how you order the math, right? If you have a normal ordering or symmetric ordering. So you can derive things like the Casimir force without ever invoking vacuum fluctuations. But as Peter Maloney, who's one of the world experts in vacuum fluctuations, he also says radiation reaction and vacuum electromagnetic fields are required for the consistency of quantum field theory. So in other words, you can't get rid of the vacuum and have quantum field theory. So you can derive the effects from radiation reaction, but you can't have a theory without the vacuum fluctuations. And I just point out here, Jaffe from MIT, people often bring this up, his paper where he does show that you can derive the Casimir effect from radiation reaction. Now, he's not the first person to do that. People did that back in the 50s. But, he also says that, the paper is not about whether vacuum fluctuations are real or not. So he's not saying, hey, they're not real. And people use this to claim that they're not real. And that's not what he was saying. But so I think it's really important to remember that it's still an open debate as to the reality of vacuum fluctuations. So now if we want to think about generating forces from the vacuum, go from, well, maybe it's not real, but how do we generate forces from it? And this is from Shan-Hui Fan's work and comments, that if the vacuum has translational and rotational symmetry, and it's in equilibrium, thermal equilibrium, there's no net force or torque. And that comes from a fundamental free energy argument of symmetry, and it's independent of the physical model details. So in other words, it doesn't matter if you're using quantum field theory, classical physics, a different theory like pilot wave. From these energy arguments, if the vacuum is symmetric and you're in equilibrium, there's not going to be any force or torque. So you need to break one of those assumptions to obtain thrust or energy. So you can either have a non-equilibrium system, such as an asymmetric potential, or a thermal distribution where there's a difference between the temperature of objects or temperature of the vacuum and an object. And so those are actually the two things I'm going to be talking about that we have studied quite extensively in looking at how to generate forces. And it's also interesting, you can also think about, well, can the vacuum symmetry be broken? And I think we'll hear some about that from Sonny White later. And there is some really good indication that the vacuum is not always symmetric, and that over certain time scales, depending upon the energy, the symmetry of the vacuum can be broken. And it's also interesting to consider, and Sean-Wee mentioned this yesterday, is that the vacuum in curved space-time does not have translational symmetry. So because curved space-time, because space-time is curved, we already do not have translational symmetry. And another thought is an accelerating body generates a thermal bath, the Unruh effect. And so that all, if you're accelerating, you're in a thermal non-equilibrium, and maybe we could take advantage of that. So those are the things you have to think about if you want to generate forces from the vacuum. Now, sort of back to the reality of the vacuum, people have measured vacuum fluctuations via coupling. So not a direct measurement of the vacuum, but a measurement of the vacuum through ways of how it interacts with other things. And so these are some fairly recent papers. This is in Science, this direct sampling of electric field fluctuations. And they, what they did, they found that the vacuum, the variance in the electric field, which they attributed to the vacuum, was inversely proportional to the space-time volume that they measured. So that's kind of interesting. By the amount of space that you correlate over and the amount of time you correlate over changed the amount of the vacuum that was there. So that's a very interesting result. And then in this paper here, they also measured the vacuum through electric field correlation using a nonlinear crystal. And they measured that the vacuum was 0.25 volts per meter. So they came up with an actual number for the magnitude of the vacuum in this measurement setup. And then if you look at these hybrid states, this paper over on the right, these are, you put a chemical inside a cavity and it's mixed with the vacuum, and it changes the behavior, the reaction rates, it changes the amount of current that can be generated, in this case in a semiconductor. So here you're seeing influence of the vacuum on behavior of materials. And now if you want to think about the asymmetry of the vacuum, so the previous work I showed kind of, indicates, hey, there really is a vacuum. And, this work that I'm showing on this chart here shows that you can make an asymmetric vacuum. And so here we have, this is a world line predicted Casimir or vacuum pressure between a sphere here and a plate here. And this is the negative vacuum pressure. So this is where the vacuum modes are not located. And you could see that it forms a asymmetric pressure distribution that I think we can take advantage of. And then folks have measured vacuum fluctuation distribution in a cavity, again, using coupling. And you could see that the vacuum distribution inside the cavity, what they measured, this is a prediction, what they measured here is also asymmetric. The Casimir force per unit area between a metal and an anisotropic material also has asymmetry to it. And some other work by Sean-Wee has shown that you can control Casimir forces with a potential difference. So what's this showing here is a sphere and a plate with different chemical potentials. In other words, a different doping in these two materials. And by controlling the potential here, you can change the magnitude of the Casimir force. So those are some really good indications that the vacuum symmetry could potentially be broken. Now, some recent results and kind of show that, again, hey, maybe we can harvest energy from the vacuum. And these results are going to be talked about on Saturday from Garrett Modell and Paul from the University of Arkansas. And I put this in, from vacuum fluctuations. There's definitely debate about that. I don't think that is, people do not agree that these are definitely coming from vacuum fluctuations. So I just want to make that clear, but it certainly appears that it is. And so in Garrett's device, which he's going to talk about on Saturday, the amount of current that is generated in this metal insulator metal diode depends on the size of the Casimir cavity. And so the number of modes that are resident here, if you look at the data here, as the cavity gets smaller, the current gets larger. And he just recently had a patent issue, not application, but actually issued based on this work. And then Paul has shown that fluctuating graphene at a constant temperature will fluctuate, and that you can generate energy, charge a capacitor from that. And it appears that, maybe that is also from vacuum fluctuations. Although, again, like I say, that is definitely not universally agreed upon. So be interesting to hear their talks on Saturday about this work. And I hope I did enough justice to the results. So what have we been doing here at the UnLAB? We've had a couple of grants on the generation of forces and energy. One is from DARPA under the QUEST program. It was called Non-Equilibrium Vacuum Fluctuation Forces. And, under this program, we predicted the conversion of fluctuation differences. In this case, it's not in thermal equilibrium, so that's where the fluctuation difference happens, will result in this particle rotating on its own. So this particle is a non-reciprocal particle. It will start rotating on its own strictly from the fluctuation differences. And we have a detailed design of an optical levitation experiment to demonstrate the conversion. This is work with Stanford, Princeton, UCLA. And the experiment would be the first demonstration that we are aware of the conversion of fluctuation differences to a kinetic force. So that would be very exciting. And then under our other grant from the Limitless Space Institute that Sunny White is running, we have been looking at asymmetric potentials for generating forces. And so our theoretical predictions show that we can get, yes, propellantless propulsion with infinite ISP because it's from vacuum using resonant tunneling diodes. Now, you do have to put energy into this system to keep the potential difference in the diode. So we don't think that conservation of energy is not an issue. And this is work in conjunction with Technion and my dear friend and colleague Yuval Dagan, who is going to give us our next talk. And so I just want Yuval, we met at the first Advanced Propulsion and Energy meeting. Maybe I'll talk a little bit about that when I introduce Yuval for the next talk. So I'm going to go into a little bit of detail about these two approaches here that we've been studying. So this is back to the DARPA program, the non-equilibrium fluctuation under QUEST. And we looked at a slew of different geometries and materials. And so the one we're proposing to do an experiment on is this doped semiconductor. It's a geotropic particle made out of INSB. So this material, when you apply a magnetic field to it, becomes non-reciprocal. And we've shown that with small temperature differences and a magnetic field, that you get small torques, but really rapid rotation and fast angular acceleration. We also looked at designs with the Weil semi-metal particles that you heard a bit about yesterday. And these are the Weil semi-metals. You can get non-reciprocal behavior without an applied magnetic field because they have an internal magnetic field. And you can get much larger torques out of these type of materials, but they're really hard to build at this time. So we are not focusing on trying to experimentally demonstrate that because of the difficulty in building the materials. We also looked at, rather than just a sphere by itself, a sphere that is above a gyrotropic material, the doped Innsby material with a magnetic field. This is the non-reciprocal material here. And then in this case, you can get motion of the sphere that will travel along above the surface. And so again, you know, small forces, but you know, clear forces of fluctuation differences, again, going to kinetic motion. And so you can also use anisotropic particles like a Janus particle where you have two different materials, in this case, gold and silicon oxide, or you can have shapes, and those will start rotating, but the acceleration is really slow. So these things will start rotating, but extremely slow versus our gyrotropic particle. And macro scale, again, the acceleration is really low. So those are some of the things we looked at, and we focused our experimental design again on this single gyrotropic nanoparticle. And just to emphasize, it converts thermal energy from random fluctuations to kinetic energy in the rotation of the particle. And you can see that, how that happens in this Poynting vector distribution. So here we have the sphere without a magnetic field applied, so it's completely reciprocal at this point. And the energy, the Poynting vector, is uniform as a uniform distribution. Now, when you apply the magnetic field, the gyrotropic Innsby becomes non-reciprocal, and the fluctuations have a preferential distribution to them. And you get this here, you see the Poynting vector, and that's how you get the rotation. And so you can look at the amount of power generated. We did some of that. It's actually quite a bit of power, which is interesting. It's more, I forget the number, so I'm not going to quote it, but quite a bit of power. And interesting, it begins rotating on its own. You don't have to start it, nothing. It's start rotating on its own and get to really high speeds, terahertz frequencies. This thing will rotate so fast that the particle itself will not be able to hold itself together. It will come flying apart because it's rotating so fast. And then I just want to point out again the Weil semi-metal materials, that they have a much larger non-reciprocal effect, kind of, you know, 3 orders of magnitude larger. So that's why you can get much larger forces out of these Weil semi-metal particles. And here's the geometry again of the sphere plate. And you have the plasmons in the material. And in this case, it's a dielectric particle. And that's where you get the forces from. And this work is, I think it was just published in PhysRev B, I believe it was. So now on to the experiment that we're talking about. And again, it's to demonstrate rotation initiated from a fluctuation difference between the nanoparticle and the environment. And we're going to use an optical levitation trapping approach. And there's a large amount of previous work in this area of using optical levitation, where you have a particle that's you know, trapped inside a beam, and you can measure really small forces and get a really good resolution. of those forces. And so one thing you need to consider is the torque drag. So in other words, there's drag on the particle rotation based on the interaction of the particle, the nanoparticle, with the air particles that are in the chamber. So you have to get the pressure down to a sufficient value so that the fluctuation induced torque on the particle is larger than the torque drag of the gas inside the chamber. And so we've done some calculations of that, what pressure you need to get to what rotation speed. And, bottom line is we can easily meet the pressure requirements that are needed to get the fluctuation torque above the torque drag. So just going over some of the parametrics that we've done, here's looking at the angular velocity versus the pressure and the applied magnetic field. So we can get a handle on the behavior and what sort of field we need to apply in our experiment. Even a small field can give a measurable result. And, of course, the consideration is how long does it take to get to steady state? We do not need steady state to demonstrate that we're generating a rotation. But you can see that some of these, sometimes like this steady state at low pressure is because it's going to be rotating really super fast. And so it takes some time for that. And some other parametrics looking at the size of the sphere. So, we've done a lot of our analysis down at 100 nanometer radius. We're going to be testing up to 2 micron, 3 micron particles, which will have larger torques, but will take longer to get to a steady state time and will not rotate. That's because the angular acceleration is less. And so we've also looked at the noise sources, the other sorts of noise besides the torque drag, like the thermal and shot noise, which are the 2 fundamental sources that we need to worry about. And bottom line is that the forces that we want to measure are well above these other noise sources. And we're also going to use lock-in detection, which will enable us to get to even lower values. And we've validated our noise predictions against published data. Here's what the experiment looks like. We have a couple of lasers, one for levitation, and then we have another laser for heating and also to do Raman detection of the temperature. So by using the Raman shift, you can determine the temperature of things. And so we're going to use that. And this is a fairly, this is a unique experimental setup. But it's all based on other things that people have done before. So we're ready to go off and do that. And I'm not going to go into detail on this chart here, but we know all the things we need to do and ready to go off and make these measurements. So that's the work on the non-equilibrium vacuum fluctuation forces. To summarize, we developed a theoretical framework for this for non-equilibrium Casimir forces in non-reciprocal systems. And we have the detailed design of an experiment for the first demonstration of the conversion of fluctuation differences to kinetic force. And those forces are above noise sources, and it's based on combining existing components. We did other things in the program as well. You're going to hear some work from Nathan Innen about gravitational effects. We looked with Alejandro Rodriguez at Princeton, fundamental limits, ideas of coupling things together, and fairly large team here of different people working on this program. And again, thanks to Mike Fitty for starting the program, and Dr. David Lewis for managing and being our champion for the effort. So the other thing I was going to talk about is our work on asymmetric potential vacuum fluctuation forces with Professor Dagan and at Technion. And this was under a Limitless Space Institute grant. And so the idea here is that a asymmetric potential, like you would find in a resonant tunneling diode, interacts with the vacuum fluctuations, inducing external forces. And by this mechanism, we can achieve propellantless propulsion. You don't, there's nothing that you're propelling other than the fields and the vacuum, and that you can get acceleration to near light speed. It takes some time, but you can get to near light speed, limited by vacuum friction, limited by what people call vacuum friction, and that's the slowing down of things by interacting with the vacuum, kind of obvious there. And so, here's a simple look at this, and this is the wave function. Here's the asymmetric potential here. Here's a quantum well, and here's the wave function, and there's these resonant modes. We're plotting all the parts of the wave function, but there's this resonant tunneling mode that tunnels through the diode, goes into the quantum well, and comes out the other side. And you can see here from this, and this is based on calculation of the Schrodinger equation, solving of the Schrodinger equation, you can see that the wave function is asymmetric on each side. It's different on this side than this side. And so that indicates that there's going to be a force there, which is, and here's an example from a real diode of this sort of distribution. But based on these calculations, so that's the idea here, is it's a resonant tunneling diode. And the vacuum, is you couple to the vacuum, it's different on one side than the other, you're going to get a force out of that. And so here's a little more detailed analysis of the different modes. And we're comparing, in this case, we're comparing a symmetric situation where things are symmetric versus an asymmetric situation. And you can see that the, in the symmetric situation, that the wave function is the same on either side. So there won't be a force there. In the asymmetric situation, the wave function is clearly different. This is a blow up of this one here, clearly different on one side of the asymmetric potential versus the other. And so from conservation of momentum, I think it requires that there should be a force there, that there should be a force. There must be a force. And so people make these resonant tunneling diodes. None of them are actually in any foundries for production, but people make these in labs and things like that. And there's different variations. And just showing some examples here, double barrier one, this triple barrier. We've based some of our analysis based on the fields inside this triple barrier array, where they actually coupled a whole bunch of these together as well. There's a strong field inside, and you can see, it may seem a little odd, but if you build these things the right way on a wafer, you're going to get a force. And depending upon how the orientation of the tunneling, the force will be in this direction or in this direction, in this case with this Sandia-based photon-assisted diode. So, there are structures that are out there, these resonant tunneling diodes that we can go off and test. And our predictions, which are based on the measured field inside that one diode, show that each diode has about 2.2 piconewtons of force over this sort of area, 0.02 micrometers area. And so, it's based on a couple of assumptions. One is that this field is coupled to the vacuum fluctuations. And so from the results I've showed you previously, of the measurement of the vacuum from the coupling to different pulses, different fields, I think it's pretty safe to say that fields do couple to the vacuum. That's really some strong published evidence about that. And then, this idea that the coupling lasts longer than the transit time through the resonant tunneling diode. Now, no one knows how long tunneling takes. People have tried to measure that. There's all sorts of data ranging from instantaneous to faster than the speed of light to some other values as well. But interesting question is also, does the coupling time change based on the energy of the vacuum that you're coupling to? In other words, if you're coupling to higher energy modes, photons of the vacuum, from the uncertainty principle, it should last for a longer time. And so versus lower frequency modes. So I think that Lawrence Ford is going to talk a little bit about this sort of coupling and the temporal sampling function. And at this time, for this analysis, we ignored the reverse modes. I should have said that here that we have waves incident in both directions. So these are, because the vacuum is going to be all around, right? So we have waves incident in both directions. And with waves incident in both directions, we still see this asymmetry. I'd say we're not taking into account all the different reflections and things like that. So there's still a lot of work to do. But if you take a look at, this, 2.2 piconewtons, and you think about building an array on a wafer, and you cover 10% of the wafer, and the sort of at the mass of a wafer, we get about 9 newtons per kilogram, which is really quite a large force. We don't know how many newtons per kilowatt. We don't think it's very much, but we don't have that number. But it's about 9 newtons per kilogram, which that's almost large enough to launch something. So it's kind of amazing. And I just wanted to point out, interestingly, from Planck's law, that above 7 terahertz, and this is something Garrett Modell first pointed out to me, is that above 7 terahertz, the vacuum fluctuates dominate at room temperature. So in other words, above that 7 terahertz, what's contributing to the black body, to the energy density, is mostly from the vacuum, not from the thermal effects. And of course, as you go down in temperature, the frequency of that gets lower. And so we're interested in, because of this, we're interested in diodes that operate up at high frequencies. At the higher, the better. And of course, we could do our experiments down at low temperatures where the vacuum fluctuations dominate over the thermal fluctuations. So, here's just a little sketch of what this would look like. You have your diode and a quantum well. There's tunneling going through there. This is using this example here. And we're going to get some vacuum fluctuation momentum that's going to move the thing. And we can enhance that, we think, by doing like exactly what Garrett did. So we can add a optical Casimir cavity. So this would have a negative vacuum fluctuation pressure in here, so a lack of modes. And, we think about it just like pressure and aerodynamics. Coming from an aerospace company, like thinking about aerodynamics. And so maybe the vacuum would act just like the pressure in aerodynamics. And then we could further enhance this by coupling in the right frequencies. So again, up at get the higher frequencies with a coupler, and people have shown these high frequency couplers and a waveguide to couple in to the material of the diode. And here's an example of a low loss epsilon near 0 terahertz waveguide that could be used to transport those frequencies preferentially. So this would be the ultimate device. And, you know, and so, hey, you know, if this force happens, how come people haven't seen this before? Well, you know, Casimir force measurements, you know, they measure attractive and repulsive forces, not motive forces. So, you know, we're always looking at, you know, like the classic sphere and plate Casimir measurement. You know, we're looking at the attraction there. If you look at all the data, and here's a more recent refined measurement where they have attractive and effective, not real, but effective repulsive forces that they've measured. But no one's checking to see if anything is moving. And that's what we want to do. And we're going to, you know, we have a series of different designs we'd like to test building up to that. And doing a cantilever measurement using either a standard AFM, or we can use a lateral force scanning probe. This is where you have a vertical cantilever, and the motion of the cantilever interferes with an evanescent wave that's going through here, and you can get really sensitive measurements. But so what we want to do is we really want to build we would like to build a resonant tunneling diode on a cantilever, and then you know, put a current there for the resonant tunneling diode potential difference, but also test it without it, et cetera. We have that whole series of tests, and people have built you know, things like gallium arsenide, et cetera, on cantilevers. And, you know, it turns out to be a little tricky to make exactly what we want based on the characteristics of the cantilever and the deposition approaches. But I think we have an approach to making one of these diodes on a cantilever. And so if you can imagine a diode on a cantilever in an AFM, put the current on, and we're going to generate a force. And so that would be something, because this would be propellantless propulsion. You could do satellite repositioning with not refueling. You can change your cross range at will, for example, as just an example of an initial application. If this really works the way that we predict, we could eliminate combustion engines for our cars, right? So very exciting. Hope we get to test this sometime soon. We're waiting to hear if we're going to get some funding to do that. So hoping about that. Okay, so just one last thought. This is a little out of the generating the forces, but I thought I would just point out that the relationship between vacuum fluctuations and biology. And if you think about our biological structures and the size of our biological structures, they are excluding vacuum modes. And so there are clearly asymmetric vacuum distributions in our biological structures. And so, you know, people in the literature have reported Casimir forces associated with cellular membranes, protein folding, the coming together of red blood cells, fatty acid chain interactions, et cetera. And so just looking at a synapse, about 20 to 40 nanometers, clearly there's going to be exclusion of vacuum modes here. Of course, it depends on the material. You know, this is not metal, but, you know, the vacuum is affecting our biological systems. And, you know, I wonder about things like maybe you've seen some of this work on stem cells. And so people build, for example, this cardiomyocyte, which is a little heart made out of a heart cells, will all of a sudden start beating on its own. And people have made these neural organoids, and they will all of a sudden start signaling on their own. And same with in the gut, they'll start moving on their own. So that's kind of, you know, is there any relation to the vacuum there? Is there, and you know, here's a further out sort of a hypothetical question. Are there DNA-like helical structures in vacuum fluctuations? You know, in other words, if the vacuum is not is there information in the vacuum, and is that information correlate to our DNA, which, by the way, is, you know, kind of sub 10 nanometer separations? And if you look at what we can build just from putting units together, and to me, this kind of comes back to what Wolfram was talking about, you know, you naturally end up with, you know, with the right constraint, you know, you end up with these spiral sort of DNA-like looking structures. So that's kind of interesting. And, you know, it's hypothesized that geckos use Casimir forces, van der Waals forces to climb up walls, et cetera, and that, you know, the potential force is really huge. So, hey, you know, if the gecko can take advantage of that, maybe we can as well. So I think I've gone, I started a little late, so maybe I did finish on time, but that's my story about vacuum fluctuations, and happy to have any sort of discussion about that. Thank you.
Before you start, so I want to point out you need to make Evan a co-host so he can help us do our job.
Okay.
And then also there's some neat comments in the chat. Aiden pointed out something missing on a slide, and there's some good links in there.
Oh, great. Okay.
Yeah, and then we may possibly be mispronouncing Yuval's name. I believe it's Dagon, Yuval Dagon.
Dagon, yes, yes, right. I'm bad. Yeah, hi, Yuval Dagon.
Is that correct,
Hi,
Yuval?
it's fine, but both ways work.
Okay.
Thanks.
I've been, yeah, I'm terrible at pronunciation.
Right, but we vowed to improve everything we possibly can.
So let me make
In our
Evan a
short life.
co-host, as you say.
Yeah, make Evan a co-host. So it's really good to see all of you. You did a fantastic job with that summary, Charles. Now, Charles, Shanwei Fan, all these people have worked so hard to really make, you know, vacuum fluctuations accessible as well as thoroughly researched. So
Yeah,
it was a great
I
presentation.
don't see Evan.
Oh, well, he's there. You come over here, right here. At any rate, I can keep doing the job. I just wanted to let you know.
Oh, okay. Yeah, yeah.
So
All right.
looking forward to your talk, Yuval.
Let's see.
And here's your
Make,
drive back for the files.
make co-host. Yay.
Fabulous summary. That was just really wonderful, Charles.
Okay, so any, I guess there's some questions in the chat. Maybe I have not been looking at the chat. Does anyone want to raise their hand, or what do you guys think? Do you think it's possible to generate these forces from a resonant tunneling diode?
Yes, hello, Martin speaking. Yeah, excellent presentation. Thank you so much. Can you hear me?
Yes, yes, thank you.
Great. Yeah, excellent talk. This resonant tunneling diode, so you are saying it will produce a force by itself without applying any kind of power to it?
No, you need to have a current to maintain the potential difference. So in other words, in a resonant tunneling diode, you have the p doped and the n doped, and there's a chemical potential there, right? And so we need to maintain, and you put a current there to maintain that potential difference. We would have to put a current in to maintain that potential difference.
Okay, so because yeah, in order to measure it, then it's very convenient to turn it on and off.
Yes,
So,
right. Then you can turn it on and off. Yes.
And if you put this on a tip of an AFM or whatever, how do you provide the power to the device? Actually, do you have any ideas on that?
Yeah. So people have made, and I went over that pretty fast. People have made things on the end of diodes. Let me share my thing again, and some pictures. So people have made temperature sensors, and so people have connected electrically across a cantilever. And there's a company we're working with up in the Bay Area that makes these cantilevers, that for temperature sensing, they have integrated the approach of how to send a current down to the end of the cantilever. Now, there's a little disconnect between the process making the gallium arsenide and the process for making the electrical contact that we're working through. But we think we're going to be able to do it. That's like a processing issue.
Excellent experiment. Good luck.
Yeah, thank you. Yes. Richard, you had a question? Hi, Richard. How you doing?
Oh, not too bad. How's things going with you guys?
Yeah,
Looks like
good.
you're doing
Good to see you.
Yeah. So on the, I guess the space that's in between these two barriers, is that a vacuum or is that a material?
That's actually a material, yes.
Okay. And you have that at ground level, right? So you don't ever try to change the potential of it?
Of the material in between, no.
Yeah.
That's a dielectric material versus a doped material.
Okay. All right. Well, that was all I really had to ask. I just wanted to get an idea of what was in between those thresholds.
Yes, yes. Okay. And Dr. Solomon, good morning.
Hi, good morning to you. What I'm thinking about is that we've really been looking, you and I and others, for this thing called inertia, the pushback, right? And I don't know if you remember, but on the back of the envelope, I showed that the Mach stuff was total nonsense, the fixed stars, and yet they still quote it in Wikipedia and every physics book, total nonsense. But at any rate, is it possible that what we're seeing in the vacuum and the various pushback we're seeing there is in fact the primal source, or is in fact what we're calling inertia?
Yeah, I mean, there are definitely papers out there where people make that assumption or make that hypothesis. That is not well accepted, but there's lots of people that think that that may be the case. I'm not sure, how would we prove that though? What sort of experiment would we do to demonstrate that?
Well, you can almost analytically start to come up with some interesting things. We're in the process of doing that now. For example, when an object's moving in space, where I'm from, it's no space, no time. There's nothing but time, space. So when you look at the time, space stuff, what you're really seeing is that this entity, this object, is basically changing a volumetric amount in time, space. And the bigger the object, the faster it's moving, the larger that volumetric amount. And that seems to be potentially calculable to some other things we're seeing.
Right.
Yeah,
how do we?
Where else would inertia come from? Where else would it come from? You see?
Right. I think that the key there is, well, what experiment could we do that would differentiate between that hypothesis and the hypothesis, say, of the Mach sort of hypothesis and the things that Woodward talks about. So I'm not sure how you would differentiate between the two.
No, the Mach's just nonsense. Just put 10 to the 22 stars in one place and determine where would it have to be in the universe for 10 to the 22 stars, all the mass plus all of the other nonsense, black matter. So, and you find out it's strictly 100,000 light years, the width of the Milky Way. So if you put all of the stars 100,000 light years away, it generates almost exactly G on a way. So it immediately gets rid of the nonsense of the Mach. Back of the envelope takes care of that.
Yeah. Interesting. Okay, thank you. Eric.
Yeah.
Hi, Charles.
Hi.
Different Eric.
Two Erics. Oh, sorry.
Eric Kammer from, you're calling in from Germany, right?
Yeah. So I'm not too familiar with your experiments other than what you showed today, but so this tunneling diode, it seems like you're setting up around the diode like a biased space time with these sort of filters that are filtering out certain frequencies. Is that sort of the idea? And you're using some sort of high frequency laser to accomplish that, or was I getting that wrong from your diagrams you were showing there?
Yeah, so it's really the, think of an electron that's in the the diode has like 2 doped semiconductors on either side of the gap of a dielectric, so that is closely spaced, that forms that quantum well. And so think of an electron in that doped semiconductor that, because of tunneling, it doesn't have enough energy to go over the potential inside there that's based on the doping, but it can tunnel through based on quantum mechanics and the ability of things to tunnel through, even if they don't have enough energy to go over the barrier. And so it's at those resonant, and those happen at certain frequencies, that tunneling. And so it's that resonant tunneling that we're going to couple into with vacuum fluctuations, just like people have done with the, the measurements of the vacuum coupling to an electric field. We're going to couple that electron that's tunneling through the diode, which is like an electric field, to the vacuum. And so, that's where the forces are going to come from. Hopefully that made enough sense.
I think so. What I guess I'm wondering is if you can get creative with how, like, to amplify this effect. Maybe you can do some sort of destructive interference around the diode, such that there's only certain regions of wavelengths on one side.
Yeah, so that's the idea. That's exactly right. So that's the idea of adding a coupler and a waveguide on one side to preferentially bring in the frequencies that are at the resonant frequency of the resonant tunneling diode. And then on the other side, creating this negative pressure of an absence, in the cavity where the vacuum fluctuations are not as numerous because some of the modes are excluded, to kind of try to draw, like a normal pressure sort of distribution, draw the vacuum through.
And what's the idea behind picking a certain frequency range for doing that? Are you focused? I know you in the slides you showed like terahertz type of frequencies, but have you thought about like gigahertz, like automotive radar type of frequencies?
Yeah, so, 2 things. One is, what is the frequency of that resonance in the quantum well, where the tunneling happens? And the other is that as you get higher in frequency, the quantum fluctuations start dominating over the thermal fluctuations. And so we would like to be in a situation where the vacuum fluctuations are the majority source of the fluctuations versus the thermal effects. So that's why we want to push up to the highest frequency possible.
Got it. Okay. Yeah. Thanks for that.
Yeah. Aiden, good morning. I think you're muted still.
Hi, sorry. I wanted to go back to the triple barrier array that you had. It was in the diode section.
Sure.
It is similar to something that I've designed or have been looking at. Let's see if because I've been working with Dr. Vallone on duplicating. It's roughly called the Manellis device, but it's a vacuum triode amplifier is another catchword. But it's conditioned ferrite, and we were getting interesting gravitomagnetic effects where it was able to recondition batteries and then provide a source of a voltage source. In effect, like the electric car, the inventor, Arthur Manellis, was able to power or recharge his batteries in his electric car without it being plugged into the grid through this conditioned ferrite. And it involves a spinning field. So in the ferrite, I don't know if you can see I was trying to share my screen. But just, is there like the triple barrier array? I'm trying to see if there's more research info on that, or
Yeah. So here's, this is the paper on that. It's some work out of Japan, I believe.
Okay.
This resonant tunneling diode strongly coupled to the cavity field. They have a few papers on it. They don't talk much about their fabrication method, but they talk about their results. And what's interesting here is they built these large arrays that are coupled together. And this triple diode, this triple barrier, has very large fields inside it. So it's like, I think I have that on the next, but this 3.6 times 10 to the 4th volts per centimeter. So inside this diode, that's a measured number. They have really large fields. So we're trying to, in our planned experiments, we're gonna build this guy and this guy here on top of a cantilever. And then a cantilever that we can send current to the diode, and then we're going to measure the forces that happen with and without the current there. And so we're looking at how to build these on top of the cantilever and the details of that, it's a processing thing, being able to do that.
Yeah, I'm familiar, or not that familiar with layering semiconductors, but I know COMSOL recently has put out a software package, and it's suite that allows you to play with the physics of multi-layered silicates and dopants and such. And then I guess the indium antimony was interesting. The fact that it starts to self-rotate.
Yeah, the INSB, the indium and antinomy.
Yeah, indium antinomy. That's a new one for me too. So.
Yeah. So they make, IR, long wave IR, mid wave IR detectors out of that material. So it's pretty commonly used. So right. So we're working to make how do we synthesize nanoparticles? People have made like teeny things because people are interested in quantum confinement. So you can find folks that make 3 nanometer, sort of radius nanoparticles out of that stuff, out of INSB. But to make a 1 micron nanoparticle, well, no one does that. And because it doesn't have that quantum confinement effect. So, but we think we can do it. We're working with a guy, Professor Dwan at UCLA in chemistry, who is going to be synthesizing those for us.
There's the Fortify 3D printer company I mentioned yesterday. There was a similar company in their next YouTube video. It was a 3D printer company out of Europe somewhere. This is all top of my head that I'm recalling, but they were down at the 100 nanometer wavelength and printing and with fine powders and such.
Right. Yeah, people are using that for making different things. So I think we better move on. We're a little bit over time, but maybe time for one more question from Eric H.
Hi, Charles.
Hi.
At the very start of your talk, you were talking about these things that would rotate on their own without any power or magnetic field or anything across them, just by them being in some type of inside of a barrier, or do you have to apply some type of power?
So there needs to be a thermal difference. So it needs to be a non-equilibrium. So there has to be a temperature difference between the particle and the environment. And so that's where the energy comes from, is that temperature difference.
Okay.
Yeah, so it's in non-equilibrium. But with using the Wiles semimetal particles, you don't have to apply a magnetic field. So just from using those particles, just from the temperature difference alone, you can get the rotation. And if you think about, the cosmic microwave background is at 3 degrees K, so there's always something there.
Yeah, that's what I was going to say. And one other thing, the wafer, you said something like 9 newtons per kilogram. This wafer, this is, I got the impression that it was unpowered. I didn't understand what you're talking about with that wafer.
Yeah. So you need to maintain a current to maintain the potential difference. So you need a potential difference. So you need a voltage inside. And so, you know, we don't think you can just, the chemical potential of the two different dope materials that's naturally there, you know, from conservation of energy, that doesn't make sense that would just stay there
Right.
as we're generating a force. So that's why we think we need to continue to add a current to that. Now, we haven't done a calculation that tells us how many newtons per kilowatt, but we think that's really, really small, because in these diodes you know, to
But they're
maintain.
already, I mean, at 9 newtons in 1 kilogram, that's almost going to allow it to lift off the ground.
Yeah,
right?
that's almost launch value of newtons per kilogram. That's right.
And the last thing I want to say is that you know, the solar neutrino flux is pretty constant day and night, and there is evidence that neutrinos can induce beta decay. And I always look at you know, is there some type of beta decay happening anywhere even close where you know, that could and obviously that's not going to happen in very many situations, but I always keep that in the back of my mind.
And you can use that to power something like this, is what you're thinking, right?
It could be, you know, it's the studies aren't you know, they're recent, so there's not a lot of data on this, but you know, beta decay is a 15-minute process, and I keep that in the back of my mind, whether it's to power something or whether it's causing some kind of acceleration.
I see. Okay. Yeah, thank you.
Thank you.
Just a quick comment. That's really important, because you just can't talk about different areas in physics and make believe they're not one or the other. But when you're talking about neutrinos, you have to talk about the Casimir and what is really going on between the two. And given their very difficult to understand nature, and I've not seen too much that goes between the two, but maybe somebody else here has.
No, I don't know much about neutrinos myself or their relation to the Casimir force, but that's interesting potential connection there to think about.